But I will do not really do some dynamical things, but more look on the singularities. So, just a small reminder, what we like to see as a translation surface is mostly we take polygons and glue them together using translations. And how I like to formulate this is, for me, a translation surface. And when we look at these pictures, we have always the type of translation surfaces we have studied, or some people have studied, for a long time. And now I want to call these types finite translation surfaces. Oh, and here's again the announcement of somewhere. I don't really need it, but so the hotel is Anja Randecker this session. Okay, so a finite oh, I just forgot what I wanted to say at first. So all of this talk is based on a very nice article. It is w.r.t singularities. Of flat surfaces. And it's written by Josh and Ferran. Okay, so I find a translation surface, x omega, is a surface connected and we have translation in the atlas. That's not all. So we have to say something like the singularities are cone-angle singularities, or what my favorite way to say this is such that when we look at this translation atlas, we get a metric. So here the singularities aren't included in this X. And when we take the metric completion, we get the singularities. And what we want is that the metric completion is compact. In fact, a compact surface. So that's what we have here, and then most of the things that were done in the last 25 years. But if we want to look at some infinite type things, then I like to drop this condition, this finite, and then I like to drop this condition here. So for me, a translation surface is a connected surface with a translation atlas. And what I want to do additionally is that the singularities shouldn't be too bad. They should be discrete. So that is set up. And what happens if we drop this condition? So we can have something that is non-compact, for example, the complex plane C, that should be a translation surface. We have a translation atlas, so everything is fine. But what can happen also is that we don't have a surface anymore. If we look at the metric completion, so one of the first examples comes from the Baker's map surface. We take a square and take the lower and the upper side, and we divide it. And then we take these two pieces and identify them. And then we take the rest and do the same. Take these pieces and identify. And the rest and the rest. And we do this infinitely many often. And we do this with the right and the left side also. And what we get is the surface. It's connected. So we have to accept all these points where we have no translation atlas, but the rest is a connected surface, and there we have a translation atlas. But if you look at the metric completion, then there comes 1 point additional. But it's only one point that will say something later. Who doesn't know this, please believe me. And if we want to look at a neighborhood of this point, that's a bit more difficult than the case we had before. So there can happen more things than only having cone angles. And what can happen? We have different types of singularities. The first one that we have seen before, this double pentagon, are cone angle singularities. And what can happen and what often arises when we only look at colors, then we can have something like cone angle singularities, but they don't spiral finitely many often around the singularity, but infinitely many often. An example is if you look at this infinite staircase. We can start with this point and look where we get. So this side is identified with this side, and this one with this one. And we start here. Something should happen here. We start with this point and we look where we get, and that fast. Okay. So, yeah, I skipped one. Okay, so we have this neighborhood. It's a fine neighborhood. Everything is okay. You can see that this one is something like infinite cyclic translation covering of a one-dimensional disk, like a finite, like the cone angle singularity, often called finite angle singularity. Translation coverings with order k. So, and then there are some links that don't look such nice, like this. These are called tame singularities. You will hear this word tomorrow in the talk. And the rest that can't be described with such a translation covering are called wild singularities. And what we see is that if we have this infinite angle singularity, we know how a neighborhood looks like, and if you have finite angle singularities, everything is clear. But what can happen for wild singularities? And to describe this isn't that easy, and that is where this article starts. Find a description of this, these singularities. It doesn't only work for singularities, but we will just look at them. We look at in which ways can we get out of the singularity, and this we are describing by space L epsilon of x, where we look at gammas, where gamma is a geodesic path. So we have it is isometric in particular. So we have such a geodesic of length epsilon. It's open, and at this point 0, we want that it starts at x. Okay, so we have something like the directions we can get out of a singularity. If we just take a regular point, we have the directions around. And what we now want to do, we want to grab this epsilon. Because if we could take one epsilon for all of them, we could find such an epsilon neighborhood, and it should be translation code. So we drop this epsilon, or say that we can choose just one. And when we identify this gamma 1 and the gamma 2, when they are the same on 0 to the smaller epsilon. So we have really something like the directions. Okay, such a equivalence class gamma is called linear approach. And we want to look at these linear approaches and now look at one and rotate it a bit around, like we did before. And if we draw a translation surface and we wanted to see what singularities, what edges contain are belonging to one singularity, then we are going around the singularity, and this is what we do in this case. So we just rotate it, and if there's another linear approach we can reach in this way, then we call them equivalent. You can do this much more formal by taking just a segment of this infinite cyclic translation covering and embed it so that we have this x at where the 0 is. Then look which linear approaches are in the image of this thing. And so we can identify some rotational components, some linear approaches, and what we get is called rotational component. Okay, if you're used to these sorts of singularities, it's not clear why we should consider rotational components, but we will see some examples. What do they look like for regular points? Again, it's just, and then this rotational components, we can, we have a one-dimensional manifold, and we can measure lengths. So going one time around the singularity or around the point should be 2 pi. And if we look at a regular point, the rotational component just looks like take r, but it's the same after going one time around. Then if we look at finite angle singularities, we have the same, it's isometric to pi k set. And for infinite angle, we can go around like r, like you see here. You can imagine we can do this infinitely often, so this is our rotational component. But what happens with wild singularities? That's the really interesting case where we could learn something new. So let's start with one example. This is a surface where we take 2 over minus 1 over 2 to the m. And we take the convex hull, and we have parallel and sides of equal length, and we can identify them. This, so on. And if we start to the singularity here, we go around and see, okay, it's the same as here, here, here. And of course, we can do this in the other direction. And we get that this is all belonging to the same singularity. And when we start at the lower point, we get this. Then we get this. So at the first view, there are 2 singularities, and I can go infinitely often around the singularities. But that's not true, because if you want to get the distance between this purple one and this gray one, you see that it's coming together closer and closer. So the distance is 0, so they are belonging to the same singularity. Because they're in the metric completion, and the metric completion, yeah. And so this is one singularity. It's not a finite angle singularity, it's not an infinite angle singularity, so it must be wild. And it has 2 rotational components. Okay. And if we go back to the Baker's net surface, was this one, we can do the same thing, and we can follow where we can get, and have this here. Then we have 2 rotational components, And we can use the same argument. Who haven't believed me 5 minutes before. All these points are belonging to the same singularity because the distance is zero. Okay, and here we have two rotational components like in the last picture. But that's not all. Because we can start with this point and going in this direction. This is a linear approach. And every linear approach should be in one rotational component. So we can look what we can do if we rotate it. We can rotate it a bit, but then there are these singularities, these edges that are accumulating. And I can't get around this, even if I take a very small epsilon. But I can't embed such a segment. And so we have here another rotational component. There are more of them in some more complicated way, but it's just an example for that we have rotational components of finite length. And what's even more complicated is if you look at this surface. No, it isn't a surface, it's a picture. And we have these segments of a circle, and what we do is we linearize it. We take I would buy a new one off the side. Okay, so we take one point in the middle, and we take the edges between. Always edges before when I went vertices. Okay, so here we take really the edges between the vertices, and then we divide these edges we have, and do this again, and then we do this with the edges that are nearest to that point and to the other one. So we do this, and if we take the limit, we get such a surface. Like in the first example, we have parallel sides of equal length, so we have translation surface. Well, look at this rotational component. We can't rotate it. It's a rotational component. We have a geodesic embedded, but yeah, there's no space to rotate it. So what can happen is that we have rotational components that are equal to one point. Okay, so we have seen examples for rotational components that are unbounded for some of finite length, for some that consisting only of 1 point. But what in the examples was every time the case was that we had more than one rotational component. That's not right for all wide singularities. It's even worse. If we look at the last example, we take a null sequence that is not converging. And then we take the plane, choose a direction, and then cut in this direction. And then we take a segment of the length of the first element of the sequence, of the second, and so on. And on the upper side, and then on the lower side, we just swap a bit. So we take here the first, the second, the third, and the fourth. And then we identify them. Okay. And when we look at the rotational, or at the space of linear approaches, and we start like this, and we go further than this, and this happens. And we can go in the other direction. Like this. So we get that every linear approach is contained in this rotational component. What you can see here is that if we go around the singularity, we can't take the same radius. If we could, it would be an infinite angle singularity. So the radius must be smaller and smaller and smaller, because otherwise we would here get into a conflict. Okay, and if we look at the length of this rotational component, it's r. And we had here that if we have infinite angle, then it's r. So that's a bit tricky. We cannot use this to to distinguish between infinite angle and wild singularities. You can occur much more things. It's not clear what everything that could occur. But we can use it to distinguish between different wild singularities to get a feeling. Because if you look at this one, that is much nicer than the one we had at the Baker surface. Okay, so what I want to see next. Okay. Then I wanted to say some other things, but last week I had a chance to discuss with Pat, and there's some work going on. And yeah, ongoing work is the most nicest, so I will say a bit about this. Where we could use this description. So, take a surface with finite area and a wild singularity. And in this case, because it's ongoing work, it's only for some special cases, the wild singularity should have one rotational component. Then it looks like this. I don't know what it looks like in this direction, but we can unroll it. Just forget that we have a translation surface. Here's the singularity every time. Here are the linear approaches, and they should be bounded and should become smaller and smaller because it's a wild singularity. Okay, so this one are the linear approaches. So if you have cell connections in that, the cell connections look like they are one linear approach going out, and of course they are one going in. So this is a cell connection. It looks a bit funny because we just forgot the translation atlas we have here, but yeah, we get such a cell connection. And what we can do now, we can signal it a bit, like if it would like on the surface. And then we can use, this is where we need finite area, that if you take just part of the cell connection and a transversal direction, and look at this direction, then it's background, and we have to get some.
Do you know on the finite area surface?
On a finite area surface, yeah. So this is where we need finite area. We could perhaps use some other things, but yeah. Okay, so we have to come back. And this is very nice because now we see, if we cut out this double connection out of the surface, we have that the surface is still connected. So this is a non-separating curve. And what we want to do now is taking shorter double connections, they exist, that do we know, and then we get some double connections here, and here, and there's something to do that these double connections don't interact this one, but it's something about getting smaller and smaller. And so we can get infinitely many non-separating curves. If we take them all together, they are non-separating because we see it, these are chosen so that they don't intersect, and in this part it's the flat part just unrolled. So we get infinitely many cell connections that are non-separating. So we have infinite genus. And it would be very nice if this would work for all wild singularities on finite area surfaces, because this would have very nice corollaries. Ask Ferran about something analytic view of these surfaces. Or what is nice is you have a translation surface with finite area, and you can say But you have finite genus if and only if x omega is finite translation surface. The classical ones. And that would be very nice. But as I said, it's just ongoing work, and perhaps it can be carried out. So, thank you.
Questions?
So in all the examples that you showed, the rotational components compared to the actual linear approaches were not significantly different. They were just closures of intervals or isolated points.
Yeah, they are one manifolds with translation structure. So you know the rotational components have to be S1 or R. So
So you can't have, for example, a rotational component that accumulates significantly more directions than were linear approaches. For example, you have a collection of linear approaches which are dense but with dense convolution. So that their rotational component is somehow adding in a lot more stuff. Like maybe a translation surface where every rational direction is a linear approach but no irrational direction.
It shouldn't exist, but it isn't now. Or do you know?
So you might try something like taking a point, drawing all the rays in at irrational angles, and then putting a puncture the rays at closer and closer points. You might do something like that.
Yep.
More converse, because that would be
Yeah.
so many similarities between together.
And what is the problem with such constructions is you want to have a manifold, so you want to be on the surface, and you want to be second countable. And if you take such constructions, you have to do these obstacles.
Right, so that's what, if you do the reverse, perhaps you put obstacles on the rational slopes,
Yeah.
not the irrational ones. Then you only have countermechanics.
But yeah, but it would be nice to know.
Well, I had a question. There's like a dictionary of the analytic counterpart. So one thing that we were discussing at some point is that, well, for cone angle singularities, the counterpart are zero, so having a differentials. How do you guys explore, say if you take your favorite essential singularity and then multiply by BC, try to see how integration what's the flat picture of this?
Don't know yet.
You don't know, but if your conjecture is true,
Yeah. Then
then it should only be an infinite angle singularity.
yeah.
Because if you have genus accumulating there, you don't have a local wiring.
That was the point I referred to Ferran talked about it yesterday.
But have you seen essential singularities at some point?
Do I want to have
Ah, okay.
more questions?